Okay, so till first order reaction we have done expression for the first order reaction, the numerical for the first order reaction, everything is done. Now the next question is that how to find out the order, how to find out, how to calculate, or how to find out, how to experimentally find out rather, how to find out the order of a reaction, the order of a reaction. I told that order is an experimentally determined quantity, experimentally determined quantity. So there are several methods by which we can find out the order of a chemical reaction. Several methods are there. None of these methods we do have to know in detail. Only thing we have to know is just the names of the methods. Okay, main four methods by which you can find out the order of the reaction. Only the concept is that what? That order cannot be found theoretically. It has to be determined experimentally. So experimentally we can find out the order by various methods. Out of these various methods, 4 of them are the important one, and just you have to know the name. Sometimes they ask you the question that name a method by which you can find out the order of the reaction. So these 4 methods you must know. Okay. The first method is named as the initial rate method. Initial rate method. I am not going to explain that. No need also. Just know the name. Okay. Initial rate method. By this method, we can find out the order of a reaction. But this method is not very much applicable. Okay. It's not that it can be used in all the reactions, all type of reactions. The second one is the trial and error method. Trial and error method is also called trial and error method. Trial and error method, or it is also known as integral reaction method or integral equation method. Integral equation method. This is trial and error method. You just try and put in the different values, different equations, whichever equation it suits. That particular is the order of that particular reaction. That's the second method. The third method is most widely used to determine the order. Just again I am saying you know the name. That is called half-life method. Half-life method. What is half-life? All of us know. So this particular method is applicable for all types of reactions. All types of reactions means for the elementary reaction as well as for the complex reaction. Hope you can remember what is elementary reaction and complex reaction. Elementary reaction means the reactions which are taking place in a single step, and complex reaction means the reactions which are taking place in a number of steps. Okay. Out of the complex reaction or in the complex reaction, the step determining step is the slowest step. Okay. The rate determining step is what? The slowest step. Slowest step is the rate determining step. This is the third method, and the fourth one is Oswald's isolation method. Oswald's isolation method. Okay. So this is also not very important. Out of that, as I told, these are the 4 methods which are used, but out of that the most important one is half-life method. Fine. So this is the first topic of today, that is how to find out the order. 2 things. One, order cannot be determined theoretically. It is a practically determined quantity. There are several methods by which we can find out the order of a chemical reaction. Out of those several methods, the 4 are the main methods. What are these? Initial rate method, trial and error method or integral equation method, half-life method, and Oswald's isolation method. But out of all these 4 methods, the half-life method is most widely used, as it can be used for determining the rate of all kinds of equation. Whenever I am saying all kinds of equation kinetically, means there are 2 kinds of equation. One is elementary reaction, which is happening in a single step, and another one is complex reaction, which is happening in more than 1 steps. What is the order of the more than 1 step, or what is the rate of the more than 1 step reaction? That is for the complex reaction, the one which is moving in the slowest speed. Okay. So slowest reaction among the complex reactions is the rate determining step. We know this. This is nothing new we knew. We just know 4 different methods. But that's all. Next is dependence of rate constant with temperature. But before going to that, Okay, fine. First we do that. Dependence of rate constant. Dependence of rate constant of a reaction, obviously, with temperature. With temperature. How the rate constant varies with temperature. Rate constant, whenever I am saying constant, for a particular reaction it is constant, be careful of that. For a particular reaction it is constant at a particular temperature. If we vary the temperature, the rate constant also varies. Okay. What is found in general? In general, what is found? First I am introducing that particular term. What is found in general? For example, the rate constant of a chemical reaction at temperature T, whatever is T, okay, suppose 25 degrees Celsius, okay, so the rate constant at 25 degrees Celsius suppose equal to X, rate constant for a particular reaction at T, at temperature T is X, okay. Now if I increase the temperature by 10 degree, if I increase the temperature by 10 degrees Celsius or 10 Kelvin, the same thing, increment whenever I am saying, the change in degrees Celsius and change in Kelvin is same, we had already done it in solution chapter, okay, so you know it. So if we change the temperature by 10, the new rate constant will be, we can write it as T plus 10, okay, that means K at T plus 10. What is found is that this value is almost equal to, is falling between 2x to 3x. Means it is doubled, it is in between 2 times and 3 times than the initial value. Okay. So if we, what I am saying, that what is seen for all the reactions, why I will come to that. Okay. First you must understand that what is it actually. Okay. So what is seen is that if the temperature is increased by 10 Kelvin or 10 degrees Celsius, the rate constant is increased. Rate constant of the reaction is increased by 2 to 3 times. So can I say that K T plus 10 divided by KT KT plus 10 divided by KT is equal to in between 2 to 3. If it is 2x, then 2x by x, that is 2. If it is 3x, that's the maximum possibility. 3x by x, that is 3. So the value will be always in between 2 to 3. Okay. And this ratio, one term I am going to introduce. Okay. Very common question. This particular ratio of the rate constant at T plus 10 to T is called the temperature coefficient. Now I will show it that how coefficient, okay, temperature coefficient. So Kt plus 10 by Kt is known as temperature coefficient. So what is temperature coefficient? Is the ratio of the rate constant at T plus 10 to T, to temperature T plus 10 to T. Okay, so that is what is temperature coefficient, and the value of the temperature coefficient for any reaction is how much? The value of temperature coefficient for any reaction falls between 2 to 3. Okay, fine. Now I will just try to explain it. I will come to the theory equation afterwards. First I will try to explain is that why this is happening. Why? I mean, how can we explain this? Okay. Now suppose there are 100 molecules. Suppose there are 100 molecules, 100 reactant molecules. Will all 100 reactant molecules undergo the reaction? First question is that. Second question, will all the 100 molecules will have the same kinetic energy? That is second question. Okay. So these two questions are actually explaining this fact. The first thing is that out of 100 molecules, only those molecules will undergo the reaction which will have minimum kinetic energy. All will have different kinetic energies, all are moving in different speeds, different velocities. Okay, if the different velocities are there, obviously the kinetic energy will be different. Now the question is, those molecules, out of those 100 molecules or 1000 molecules, whatever, out of the total number of molecules, whichever molecules are having the minimum energy, that will undergo the reaction. Try to understand now, it's very simple. Okay, I'm telling some very bad examples. Okay, don't write it anywhere. Okay, just for your understanding. Suppose there are almost 70 students in this class. Okay, so 60 to 70 students are there. Now these 60 students, if I conduct a test, now at this moment, anything, you can take it anything. I'm talking of test. You can take it of height, you can take it of weight, you can take it of whatever. Okay, so that is the natural trend that very few will fail, very few will get 90 and above. Yes, most of them will get somewhere in between the average marks. Okay, that's a common trend of everything. If I talk about the height of people, if I just take 100 people in general, and if I just measure the height, we will see very few are very short, very few are very tall, most of the people are of average height. Okay, that's a natural trend that is called Maxwell-Boltzmann distribution. We call it Maxwell-Boltzmann, B-O-L-T-Z, okay, Boltzmann distribution. That is actually happening for anything. Okay, so here it is happening also for the molecules undergoing the reaction. That means the reactant molecules. If we measure the kinetic energies of the reactant molecules, we will see that very few will have very less kinetic energy, very few will have very high kinetic energy, most of them will have the average kinetic energy. So if we plot, please understand the graph, that is everything. If we plot the fraction of molecule or number of molecule in this side, fraction of molecule means, whenever I am saying molecule means we are talking of reactant molecule, and in this side if we plot kinetic energy, please understand the graph, it's nothing, okay. What I told, that very few fraction of molecule will have kinetic energy very less, very few molecule will have kinetic energy very high, yes, but most of them will have kinetic energy average kinetic, most part of it, most of the fraction will have the average kinetic energy. Yes, that will be peak and again. So this will be the nature of the graph of anything, any variation. If you see any variation, you will see the nature of the graph is like this. Okay, very few will have the lesser value, very few will have the higher value. Only the average values will be conducted, or average values will be shown by most of them. Now I am plotting kinetic energy over here. Forget about kinetic energy. Okay, let's come back to the test. So this is the number of students getting marks. Very few are less, very few are high, most of them are in the average zone. Clear? Now there is a pass mark in the test. Suppose the pass mark is 30. Just suppose the pass mark is 30. Here we are plotting pass mark, here we are plotting fraction of students. Pass mark, fraction of students, right? Suppose the pass mark is 30, so this is 30. Suppose this is 30. Okay, so the students who are getting marks above this are going to pass. So these many students are passed, not these students, because they got less than 30 marks, they did not pass the exam. Fine, I took this as a surprise test. Fine. Now your board exam, slowly your board exam will come. It will come very soon only. You will see that time flies. Almost 1/4 of the syllabus we finished in online. Okay. So very soon you will find that you are in the doorstep of the board examination. Okay. So whenever the board examination will come, I know that at this moment whatever seriousness is there in you, the seriousness will increase many folds, much more time. Okay. Forget about our school. Our school, it's completely different because everybody is good. So I'm not talking of our school. So suppose of some general school, normal school. Okay. So board exam is coming, and everybody started studying. Whenever everybody will start studying, what will happen to their marks? Their marks will all increase or not? Their marks will all increase because they are studying now, they know more, their marks will increase. Okay, so the average will shift in this direction. Now the most of the student will get more marks. Okay, same way if we increase the temperature, now this is happening at a particular temperature. Suppose this is the energy, now I am telling it as energy. This is the energy, minimum energy which is required to pass the exam. This is the minimum energy of the reactant molecule which is required to undergo the reaction. Which is required to undergo the reaction. Okay, Navita, please unmute yourself. Which is required to undergo the reaction. Okay. Now as the number is increased, as the temperature is increased, what will happen? The kinetic energy will be, the average kinetic energy will be shifting more. So if we increase the temperature, by 10 Kelvin or 10 degrees Celsius, then the curve will become like this. It will become flattened. Why flattened? You can understand that. What happens now? Average people are going to this side. Means now more number of people will pass, more number of reactant molecules will undergo the reaction. Okay? But this energy, the pass mark, is remaining same only. The minimum energy that a reactant molecule should undergo the reaction is remaining same only. But the fraction of molecules that is undergoing the reaction, is now increased, and that is increased by 2 to 3 times. The volume of the first part and the volume of the second part is actually twice to thrice more than that of the volume of the first part. And that is the reason for which the rate constant increases by 2 to 3 times. Now I am coming back to this energy, which is the minimum energy required by one reactant molecule. Please understand it. One reactant molecule to undergo the reaction. E is what? E is the energy that is required or that must be present in the molecule, in one molecule, to undergo the reaction. Generally we represent it by E star, not by E. We represent it by E star. So what is E star? E star is the minimum amount of energy that is possessed by a molecule to undergo one molecule, okay, to undergo the reaction. Whoever has got lesser energy than that, they are not going to undergo the reaction. This particular energy possessed by one molecule is called threshold energy. Okay, so pass mark is what? Pass mark is nothing but threshold energy for the reaction. It has to have threshold energy, then only it will undergo the reaction. Okay. Now, if it is 1 mole molecule, if it is 2 molecules, what will be the total energy required? 2 into E star. If it is 5 molecules, total energy required is 5 into E star. If it is 1 mole of molecule, the total amount of energy that is required is Na into E star. Na is what? It's nothing but Avogadro's number. 1 mole, Avogadro's number, into E star. E star is the energy that is possessed by one molecule to undergo the reaction. Okay? And this total energy is called activation energy. You have heard the name earlier maybe, but you don't know. Again listen to this. Okay? Activation energy we are representing by EA. So what is activation energy? Now let's define activation energy. What is activation energy? It's the amount of energy required by, or minimum amount of energy I should say, required by 1 mole of a reactant molecule, right? 1 mole of a reactant molecule to undergo the reaction. What is threshold energy? You understood the difference between threshold energy and activation energy. Threshold energy is the amount of energy that is required by one reactant molecule to undergo the reaction. Whereas activation energy is what? It's the minimum energy required by 1 mole of reactant molecule to undergo the reaction. Okay, so that is activation. That must be the difference. You must know the difference between the activation energy and the threshold energy. Fine. So this is very arbitrarily, very fatly, you can say, not very quantitatively. This particular explanation is given, that he told that it is in between 2 to 3. In between 2 to 3 means anything. So many things, okay, not very quantitative. This particular determination of variation of rate constant with temperature, that is our we are doing actually variation of rate constant with temperature, that is our heading, okay, is not very quantitative. Hence comes a scientist called Arrhenius, okay. He gave a very much quantitative representation between Arrhenius, okay, equation. Okay, he did an experiment, I mean a lot of experiment, and he gave the what did he say, the relationship between the K, that is rate constant, and temperature, how it is varying with temperature, very quantitatively. And this equation is known as Arrhenius equation. There is no deduction, just the equation you have to know, and then from the equation we have to come to another form, and then we have to solve the numericals related to this equation. Plus, so Arrhenius equation says that K is equal to, so the question that can come is that write down Arrhenius equation mentioning what is what. Okay, K is equal to A into e to the power minus A by RT. K is equal to A into e to the power minus A by RT. That is Arrhenius equation. What is K? K is rate constant. A is called frequency factor. That's a constant for a particular reaction. A is a constant for a particular reaction, and that is known as frequency factor. Hope you are noting down frequency factor. E is nothing but log to the base E. We call it eccentricity constant, exponential constant. You know this. That is log to the base E. Okay. That means ln. Whatever we write, ln is E. Okay. EA, just now I told it's nothing but the activation energy. What is activation energy? You have the physical concept of that activation energy of the reaction. Okay, of the reactant molecules. R is nothing but ideal gas constant. R is nothing but ideal gas constant, and T is temperature in Kelvin. Temperature in Kelvin. Okay, fine. So now how quantitatively it can explain the thing? See, we are going to do a very simple mathematics, very simple mathematical deduction. You are going to do with me, and once again you are going to practice. That's all. So we are going to take the logarithm of both sides. Obviously natural logarithm we are going to take because here is E is there. So I am going to write ln k equal to ln whole thing, ln A into e to the power minus A by RT. Now you know log AB equal to log A plus log B. Log AB equal to log A plus log B. So we are going to write it like this, ln A plus ln e to the power minus A by RT. Can I write it? We can write it, right? Just taking the, you must write before that, taking the natural logarithm of both sides. Taking the natural logarithm of both sides. Taking the natural logarithm of both sides, we get ln k equal to ln A plus ln e to the power minus A by RT. That is equal to, or you can write next one, ln k equal to ln A. This is what? Log A to the power x equal to x log A. We know it. So it is minus A by RT ln E minus A by RT ln E to the base E. Log E to the base E is nothing but 1. Ln E is 1. Log 10 is 1, but ln E is 1 because log is to the base 10 and ln is to the base E. Okay, so ln E is 1. So this equation is becoming like this. Now, next line you write, converting it into arithmetical logarithm. Converting the equation into arithmetical logarithm. Converting the equation into arithmetical logarithm. We get, so obviously if we convert it, it will be 2.303 log k equal to 2.303 log A. Just converting the ln into log minus A by RT. Minus A by RT. Okay. Now right, as I told, it's nothing. As I told that if you tell me to do it at 3 o'clock night also I can do it, but you are doing first time, so you need a little bit of practice. So that's all. A simple mathematical derivation. Next you write dividing both sides by 2.303. Dividing both sides, just to simplify it, that's nothing. Dividing both sides by 2.303. We get dividing both sides by 3.303. we get, what do we get? If we divide this by 2.303, it is log k should be equal to log a minus a by 2.303 RT. Will you get this? Log k is equal to log a minus a by 2.303 RT. We'll come back to this afterwards, but before that, first we are going to try to plot it in graph and try to get the value of k. Just see, if we plot now log k in the y-axis, I already told you several times, I told you must have the concept clear. Log k in y-axis, so log k is equal to y. Okay, varying with, we are trying to understand the variation of k with t. Here t term is there. What t term is there? 1 by t, right? 1 by t, 1 by temperature we are going to plot in the x-axis. Yes, 1 by temperature we are going to plot in the x-axis. So what is this? Minus EA by 2.303 R. So this is x. Minus EA by 2.303 R is nothing but m, that is the slope. And log A is nothing but the intercept. So this will be an equation of straight line again. We have done it several times. Now hope you can understand that. So this is an equation of straight line with the slope how much? Minus EA by 2.303 R. Minus means the negative slope. Negative slope means the straight line will be like this. Yes, the straight line will get a straight line like this. Okay. The slope of it, how to calculate slope, I told you again for several times. Just draw right angle triangle, measure the perpendicular, measure the base. Perpendicular by base will give you the value of slope, and the slope of this is how much? Slope of this is equal to minus EA by 2.303 R, right? Minus EA by 2.303 R, that is slope, right? We know the value of slope from the graph. We know the value of R. R is ideal gas constant, so the value is known. Can we find out the value of EA from the graph? We can find out the value of EA graphically. Then if we extrapolate it, that also you know, if we extrapolate it, okay, it will cut the y-axis, and this value, that is the intercept, is what? The intercept is nothing but log A. What is the intercept? Intercept is nothing but log A. So if we know the value of log A, we can very easily find out the value of A. This is the graphical representation of Arrhenius equation. Now again we will come with this equation to the mathematical representation of it. But the time is not going to permit. Okay. Anyway, let me just try mathematical representation of it. So suppose at temperature T1, the value of rate constant is K1. At temperature T1, the value of rate constant is K1, and we change the temperature to T2. The value of rate constant is K2. For the same reaction. Now first condition, T1, when T1 rate constant is K1, we will put in this equation, the Arrhenius equation final form. So what we are going to get? Log K1, see, it's very simple. Log K1 equal to log A, as I told, A is constant for a particular reaction, minus EA is constant, pass mark is constant, 2.303 R is constant, and what is left is T1. Can I write down this for the first case? That log K1 equal to log A minus EA by 2.303 R T1. Same way, when the temperature is changed to T2, can I write log K2 equal to log A, because A is constant, EA is again constant, divided by 2.303 R T2. Simple, very simple deduction. It's nothing very tough. Okay. from these two equations, if I now just subtract it, that means 1 minus 2. So this is minus 1, minus, this is plus, right? If we do this, what we are going to get? Log k1 minus log k2. Log k1 minus log k2. In whichever way you write, doesn't matter. You can write k2 minus k1 also, no issues. That is up to you completely. But what you are doing, that must be correct. Okay, the sign, only thing the students are doing the mistake over here with the signs. Be careful about the signs. So log k1 by k2 is equal to log of k1 by k2. Log a minus log b is log a by b, we know it. Equal to, this is cancelled. Log a is cancelled. What is left now? EA by 2.303 RT2 minus EA by 2.303 RT1. Okay. So what is common over here? Can I say EA by 2.303 R is common? If you wish to take minus common, you can take minus common. I took plus common, doesn't matter, it's up to you only. EA by 2.303 R, if I take plus common, then what is left over here? 1 by T2, right? 1 by T2 minus 1 by T1. Okay, this is the equation, quantitative equation for the variation of rate constant, with temperature. Now suppose you are told that the temperature at 25 degrees Celsius, the value of K1 is something 300. What is the value of K2 at 50 degrees Celsius? Given EA is equal to this, we can do it. That is the type of questions. Okay, fine. So hope you understood that.